All right, welcome. This is going to be another video where I practice the recursion tree technique. And if you took a look at my last video, I went into a little more detail. Now I'm just going to go and practice it by doing another example. Okay, so again, to get us started, this time I've got a slightly trickier one. I've upgraded my term here. It's now got a non-1 term out front. Still dividing by 3. I thought that might be good. And now I've got an n squared function out here, so a couple different things to work with. And let's just go ahead and practice. So the first thing, sometimes I draw them. Might as well draw it a little bit. So I guess this is my tree. I'll start with my root. And I'll maybe just draw a couple levels because these trees get pretty big after a while, especially when you have 4 nodes on the next level. Now, how did I know to draw 4? Is because there's this 4 out front. Now, often if you get, a little bit of practice with the technique, you don't need the picture anymore because you kind of know how the 4 factors in, and I'll show that when we get there. But just to make sure, we'll see that the next level down gets another 4, and another 4, and so on. And so I guess on this one, we'll have a total of 16. And maybe we can start filling in our table a little bit. I usually start with the level. I give these a level a name so I can keep track. This would be 0, 1, 2. And then I'm going to have my size. You don't have to keep your columns in this order. I just have been doing this for a while, and this is the order I go in. Size, n, is our starting size, almost always. I really can't think of a good case when that's not the case. And so then we look here, so size is what factors in here when we look inside the term of the t term, the recursive term. T is usually our recursive term. We look inside there. That's going to determine what our size is as we go down the levels. Now, usually in the kind of recursive terms you're going to look at in a divide and conquer design strategy, you're going to see divided by, often common, divided by 2 probably most of the time, or maybe divided by some other power of 2, divided by 4 or 8 or 16 would be common too. Divided by 3, not as common. You might show up here and there in your analysis, but it's not as common because often dividing things in 3 is no more advantageous than dividing it in 2, and so usually we'll do that. But for my example, I thought, hey, why not divide by 3? So I've got divided by 3 here, and in this case, we're only considering what's inside. We're saying, what's the size on each level as we go down? Now, why are we extracting that out and focusing on it? Because in a second, we're going to plug it into this, which is our cost. And maybe I'll just go down to the next level. Remember, we're trying to identify patterns. So whenever possible, I like to keep things, even though this constant could be simplified to a 9, I'm going to keep it in this format so that I can save that pattern, isolate it when I get lower down to a level where I want to keep that pattern in mind. Okay, level, size. What were we talking about? We were also talking about the number on each level. The number. So if you want, you can call this number of nodes, but I usually just put the number sign there. And the number on the first level is always 1. That's presumed, unless you're, again, looking at a bizarre kind of case. It could be something different in a bizarre case, but for the non-bizarre cases, we've got 1 here. But then this, so maybe I'll draw another little arrow here. This is where we determine, or where we get the number progression. Out of here, we get the size out in front, tells us how many then. Okay, now 4. And then again, 4, if each of these 4 had 4 children of their own, that's 4 times 4. And again, let's leave it in that form. Let's leave that pattern there so we can identify it, keep it. Again, when we get down to level I, we're going to want to extract that. Okay, so this is the number of nodes. And then we might have the cost per node. And remember, that's because in a second here we want the total cost. And the total cost is just multiplying these two together. Maybe I'll write it like that. Okay. So my cost per node is what's given here, with the exception, and this is the part that I think some students sometimes forget, is we need to plug the size into the cost. We can't just copy this down. Okay, we need to plug in the size, meaning this is the cost on level n for how big for the cost for when we're at size n. But as our size gets smaller, the additional work we do also gets smaller, presumably as long as we have this function of n has an n in it. In this case, our cost per node, so our first time around, we can write down, yes, our 6n squared, but we don't want to just write 6n squared again. That would be wrong. At least it might simplify it in a second, but at this point we want to be careful. This should be over, and now I want to be very careful. I want to write 3, but if I write 3, I'm being sloppy again. Okay, how am I being sloppy? Maybe see if you can see my mistake as well. Is I need to plug my n over 3 into this function of n, but that n is squared here, which means the 3 here needs to be squared as well. And maybe I'll leave it like that. Who knows what's going to be helpful in my pattern and what won't. I'm going to leave it like this. Okay, now my total cost is the multiplication or the product of these two columns. So that's 1 times 6n squared here. We'll get 6n squared. That's 4. Again, I'm going to leave all my pattern stuff. It's going to be messy for a bit. Some of us might just be used to simplifying this stuff down. And I don't blame you, because why carry that all around if you can start canceling and so on. I'm going to leave it all as is, because I want to know where each piece comes from. Okay, eventually we're going to have a formula we'll have to figure out for this next bit here. Okay, I was doing this already. Let's be careful again. Now I need to plug in n over 3 squared. So if I'm being very careful, I'm going to still have my 6. That doesn't change. We're going to get an n. We still have an n squared, it looks like. But now what are we dividing by? 3 squared all squared. So 3 squared all squared is 3 to the 4. And again, I guess I need a lot of space over here. I got 4 times 6n squared all over 3 to the 4th now. Now, sometimes the pattern when we get down here to level I am not gonna draw the level here. Often I'll just draw a little box with a squiggle in it anyways, because there's a lot down here. How many are there down here? Well, let's go down this column and see. If on level 2 there was 4 squared, then on level I, there must be 4 to the power I. And then same thing, let's find the pattern on the size. How big are we now? Well, if on level 2 we were at n over 3 squared, on level I we must be n over 3 to the I. So you see we're trying to find these patterns now. This pattern here, this is the one that might be a little bit more challenging. But if we see 6n squared, 6n squared, 6n squared, we might even let's just grab that whole part and pull it out, 6n squared. And then what? We have 1 over, now this is the part here. Well, this is over something to the 0, because that gives us the 1, right? This is over something to the 1, but it's 3 to the 2. So it's actually 3 squared, so I'm going to actually write that as 9 for now. I don't know if that's going to be helpful for me. Maybe I should have left it as 3 squared, but I'm going to write it as 9 for now, because it allows me to see that really I'm raising this thing to the I. Because on the next level here, you see, if I was writing this in terms of 9, I could write this, I'm going to rewrite this as 9. Then this one becomes 9 squared. And now I'm getting a pattern that matches. So I'm going to extract that out here. And now putting that all together, all right, we've got 4 to the I times 6n all 1 over 9 to the I. Okay, that's probably about as messy and nasty as you're going to get when you have this kind of function. Partly because, and this is slightly by design, and I'm sorry, well, maybe I'm not sorry, because the purpose here is for us to learn, and so I picked something that I knew would get a little bit tangled down at the end. Often we get canceling out between this thing that goes to the power I and this thing that goes to the power I, but unfortunately here we have 2 times 2, prime factoring of a 4 is just giving us 2's. This one's giving us 3's. There's nothing to cancel out. There's nothing for us to cancel out. We could maybe cancel out some 1, 3 out of here, but I'm going to leave that 6 alone. It's tangled enough as it is. I'm going to leave it alone. In fact, we might even pull this out. In fact, maybe I will just rewrite this to simplify it one more to make it look a little bit nicer. We could put that 4 inside the bracket here. And that actually might be the easiest or the simplest form. Actually, I think it is. Okay, we'll see in a second why that's going to help us out. Okay, remember, we're not quite done here. We need to keep going down until we get to, I usually call this level K, the last level. Now, my last example in my last video, I didn't need to solve for K. In fact, I showed a little trick at the end that said, hey, we could imagine K was in infinity. We could imagine we went down infinite levels here, and it would still only cost us this much. And so I left it at that. But usually we need to solve K. We need to know what K, maybe this is the same case here. Actually, I'm not certain. We'll see. So we might have to solve for K. If not, well, we'll do that in another example. Let's finish off here though. What size are we going to have here? Well, again, I usually look up here to see when do we trigger our terminating case. In this case, it says less than or equal to 1. Now, I'm going to write this in two ways. I'm going to say, first of all, this pattern that we identified on level I is still going to apply on level K. And that's going to be important in a few of these columns. But in this column, we could write it as n over 3 to the k, and I'm going to again use this here, okay. If this is the size, well, we're assuming it's less than or equal to 1. Now this is the part that actually might be a little bit more important to us right now, but in a second when we might want to solve for what k is, this whole thing, I guess, will factor in more. Okay, we might want to remember that what we've been doing is dividing by 3 all the way down. Now this row is going to factor in considerably. This 4 to the I becomes 4 to the k. This tells us how many of these terminating conditions we have on the final row. How many of these what? How many of these 11s? Because the cost here, the cost per node on that final level is no longer given by this pattern we've identified. It's now given by just this 11. Okay, now depending on what you've got in your own work, that might be a known constant like 11, or it might just be a name like C or D. Okay, continuing along, what's this last bit? We simplified up here, but the last bit, remember, is just the product. Well, I could just write that as 11 times 4 to the k if I want. Now it looks like we'll probably need to know what k is to simplify this term. We'll see if we need to know to simplify the sum as well. Let's go ahead and try and tackle this. Now remember, we're now done the building the table part. But when we use the recursion tree technique, building the table is sort of, I'm going to say about 70–75% of the way there. If we can get this far, we've got the pieces. We need to put them together. And again, usually I like to draw little squares around them and remind myself these are the pieces. Why? Well, if I kind of draw my wiggly square around it, this is the column that I'm trying to add up here. Okay. Now this, of course, is just our expression of this was our simplification of this expression. So putting this together is going to create, well, I'm going to put a little equal here for 2 terms. Now I usually put this term first because it's usually the simpler one. This is 11 times 4 to the k. And my second term is going to be a sum. This is the term we're going to sum over, so we got ourselves 6n, and we simplified this out already enough that actually that 6n could have popped out, which was convenient, but I'll leave it as it is for now. We've got this, and just remember, how do we come up with our indexing for this sum? That's why I usually leave this level in there. This one sometimes you might leave out and say, I know how to count. But this one reminds me that I'm at I, and it goes from where? 0 until k by k minus 1, because level k we already handled. This is level k right here. Okay, putting this together, a little bit of simplification. I might do this one first. So again, 11 times 4 to the k plus, let's bring that 6n that I said we can outside, I equals 0 to k minus 1. Well, 4 over 9 is less than 1. So because it's less than 1, we can still apply the Zeno's paradox, or the fact that this sum, if we change this to infinity, is still going to be less than a constant. So this term here, well, I'm going to simplify that term, and maybe if I'm going to do a less than or equal to here, I'm going to still leave my first term alone. This term here, I'm going to say is, I'm going to just merge that 6 in with whatever constant I get out of that, call it c, and multiply that by my n. So now it seems like what's really going to matter here is this term here. Okay, this term here. How does it interact with this term here? Is it greater than n or less than n? And that depends, of course, now on k. So let's go back. Where was our little formula here? There we go. So we had something like this. N over 3 to the k is less than or equal to 1. Okay, now there's a couple cases where we can sort of consider this. Now, sometimes it's convenient here. Now, I usually leave it as 1 here. Sometimes it's convenient. This is where another place I like to say I kind of blur my eyes. I know I'm going for a guess. So if I really try and solve for this, there might be a floor or a ceiling involved, or there might be a -1 or +1 involved. I'm usually going to throw those away in my guesswork anyways. They clog things up. So I usually just say, let's imagine this was an equals, because I can solve that one pretty easy. I'm going to take this n equals 3 to the k. See, I just multiplied both sides by 3 to the k. And then do log base 3 of each side. Going to give me log base 3 of n is equal to k, because of course logs and exponentials cancel out. So we're going to do that. We're going to get our k equals log base 3 of n. And now I can plug that in here. So that's going to give me 11 times 4 to the log base 3 of n plus our cn. And what do we do with that? Well, again, it depends on what formulas, what rules we remember about our exponentials. But usually the important exponential rule here, there's two. It depends on how you remember it. Let's do a little scratch as well. I'm going to just pull that out. 4 to the log base 3 of n. Well, the important thing, or the rule that I guess I will prove to you, the rule that I like to remember is that we can swap the 4 and the n. So we can get n to the log base 3 of 4. Now this, we can all sort of quickly identify is a constant. That's a constant. So what we're looking, or what we're dealing with here, is a polynomial, and I'll talk a little bit more about that in a second. But how can we be sure that this is true? Well, we can write this. This works better when we've got some bases that we're pretty comfortable with, but these ones don't work out. This is not giving us a constant that is a friendly constant. This is an ugly constant in the sense that it's irrational. But let's go ahead and just try and solve this using maybe some log rules that we're more familiar with, and exponential rules that we're more familiar with. One of the problems here is that 3 and 4 are not the same base. If the log and the base of our exponent were the same base, bingo, we just cancel them out. We're good. So really, the effort we need to do to change, one of these into the other is just change the base. Can we change the base? Now, which base do you want to change? I'm going to tell you straight up, I could probably change the base of the log, but I'd have to guess for how the formula works, because I don't do that every day. But changing the base for the base, changing the base of the base, is easier for me. I remember that math, so I'm going to go that way. If you remember log math, because I don't know, you've got log logarithm rules tattooed on your arm, then you can just go and look that up quite easily. I don't have that particular tattoo, so I won't be able to do that one. So I'm going to take this 4, and what do I want to do? I want to turn it into base 3, which means it asks me, well, what 3 to what power gives me 4? 3 to what power gives me 4? Now, hopefully some of you already know the answer to that, but I'm going to let the rest of you try and think for a second. What does 3 to what power, what does it gives you 4? Now, I've given you a little hint, I give you a little space here. It's obviously something I got to write here, because 3 to the power 1 gives me 3, and 3 to the power 2 gives me 9. Hopefully we're all got that far. So 3 to the power of something that gives me 4 has to be between 1 and 2. That far. Okay. So I don't know. So far we've narrowed it down to some d, some exponent d that's between here. Now, of course, this is why logs were invented. The number is log base 3 of 4. It's a weird number. It's in between 1 and 2. Sure it is. But it's log base 3 of 4. Now, how do I know that? Because logs and bases of our exponential functions cancel out, right? So we can cancel those back out, and what do we get? 4 again. That's what I wanted, right? 3 to the log base 3 of 4 is just 4 again, okay? And again, that's because exponentials and logs are inverse functions, just like plus and minus, and just like multiply and divide. If you multiply by x and then divide by x, you get back to where you started. Just like if you raise it to the exponent and take the log, I did that backwards, but take the log and raise that to the exponent, whichever way you go, it doesn't matter, forwards or backwards, you get back where you started again, okay? But this little bit on the outside comes along for the ride. Now, we were trying to turn it into this, not turn it back into itself. We can go back and forth algebraically between these two forms all we like, but it never gets us where we were going, which was up here. How do we get up there? Well, now we remember that how we work with these exponents, because what do you do when you have two exponents like this? Something to an exponent raised to another exponent is you multiply them together. You multiply your exponents together. Well, the next step I'm going to do with that multiplication is remembering that multiplication is commutative, which means we could swap them. The order that we multiply them doesn't matter. So I'm going to continue my math down here because I did a little aside about my d. We're down here. We're going to have 3 to the log base 3 of n, all to the log base 3 of 4. Now, take that, the inner bit, and now do the cancel out. That gives us the n to the log base 3 of 4, which was what I said my form was of the rule that I promised at the beginning, or that I did up at the top here. This rule is the one that I remember because I've had to do this bit so many times that now I've remembered this bit that I don't have to do it anymore. I just remember the rule. And in fact, you might have this on a list of rules already. Or sometimes I notice this doesn't show up on the list of rules that you might be given by your calculus teacher or something like that. And that's partly because maybe your calculus teacher is not a computer scientist. And computer scientists are the only ones who are going to be dealing with this kind of stuff on a regular basis. You might see this as in other areas of science that I'm not super aware of, but in computer science you're going to see this a lot. So you're going to want to know how to solve this. So this particular log rule is one that I remember. Why? Because it changes something here that looks suspiciously like an exponential, but I know it cancels with logs, but my bases aren't the same, so I'm not exactly sure how it's going to cancel out into something exactly what I know it is, which is this is a polynomial. This is n to a power, and this power, even though it's an ugly irrational power, is just a constant, a positive constant. Now that brings us to the question, which positive constant is it? Oh good, I've got it right here. This is all I care about. It's the positive constant that is bigger than 1 and less than 2. And again, remember that's because we know that log base 3 of 3 is 1. That's what we have here. And log base 3 of 9 is 2. That's what we have here. So log base 3 of 4 must be between 1 and 2. So let's finish off. We're going to take this now, and we're going to plug, or we're going to swap that around. First of all, we've got n to the log base 3 of 4, and we've got cn. So we've got 11 n to the log base 3 of 4 plus cn. And we really have one question left, which is which of these is bigger, meaning which of these is the dominant term. And the question then becomes which of these exponents is bigger. And that was answered by this question we asked up here, which is log base 3 of 4 is greater than 1. So this must be, or at least a good guess here, is n to the log base 3 of 4. And I'm not going to change that any other way, because log base 3 of 4 is an irrational number, which means if I write any number there, it's going to be an approximation, and why not just write it as it is exactly, and that's log base 3 of 4. And that'll be my guess. And again, if you wanted to, let's just run that through the master theorem and check. Let's go ahead and do that, because I've gone and done all this work, and I made an error. And often when I make an error, especially when I'm making a video like this, I'll just say, well, oh well, way to go, dummy, made an error. Of course, that's not the right way to think. We all make errors all the time. And what should we do when we make our errors? We should fix our errors, right? We shouldn't call ourselves dummies. We're great. We know math, among other things. So let's not beat ourselves up about it. So how would I do that? I mean, I just said, let's check this with the master theorem to make sure we did it right. And then I thought, oh no, it's wrong. Why? Because I can do the master theorem a little bit quick, but let's do it together. I do a couple steps here. So I'm just going to re-jot us down here. We had 4t n over 3 plus 6n squared. If I'm going to do master theorem of this, I'm going to do a, which is my 4. Remember, we're doing the same math that we were doing up here in the recursion tree method, so it's sort of, this is a good exploration. We're grabbing this same number we were grabbing and putting into our number column. That's why it shows up in the master theorem. What other number do we have is b, which is this one, which we were plugging into our size column, okay? And it gives us, and it was a 3, sorry. And then, depends on which version of the master theorem you've got, and I've got a couple different versions I work with, but sometimes we'll just grab that whole thing and call it f of n, 6n squared. Now the version that was first proven by Corman, Liserson, and Revest tells us let's compute a function right now, and it's actually an important function because it's this function. It says go and find n to the log base b of a. So b is 3, a is 4, so this is n to the log base 3 of 4. That's exactly what we got up here. And then it says compare that function to this function. That's what the master theorem tells us. And whichever function is greater is the dominant function. But wait a second. We just compared n to the log base 3 of 4 to cn in our math, not n squared. If we had to compare it to n squared would win because of the same math we just did up here. So which is it? Our math said n to the log base 3 of 4 wins. Master theorem says n squared wins. So which one wins? Master theorem. Well, of course, because the master theorem is called the master theorem, and it's master. No, that's not why. We should trust our math. We're the ones who did the master theorem. We made a mistake somewhere. So where did we make our mistake? Now, what would I do? Well, what did I do when I saw my mistake here? And for a second, instead of continuing my video, I sat in silence and said, well, gee, I got the wrong answer. Why? What did I do wrong? So I went and I found it, and then I thought to myself, well, I'm going to go delete all that part of the video where I screwed it up, and I'm going to go and I'm going to re-record it like I never make mistakes. Of course, that's not a good idea. And then I started thinking, well, look at how much I'm going to have to delete. How far back am I going to have to go? Maybe I should just re-record the whole video. But then I thought, no, because, well, here's what I would have done if I did this in class. I would just go Well, this is where I made my mistake, right here. When I went from this row to this row, and some of you who are watching might be going, well, duh, I saw this mistake a long time ago, and I did the math myself. And as I followed along, I realized that as that n keeps going down here to here, I would not make that mistake. I put a 2 in there instead. Okay, so instead of going back, deleting everything I did, recording a new video, I'm going to show you how I found my mistake, because this is probably more valuable for you if you're making a mistake in your own work and you come back and you say, but wait, I double checked my work, I made an error, how do I know which is correct? And this is not just true for recurrence relations and the master theorem, but there are usually multiple ways to do any problem in mathematics. So one of my tricks when I was learning mathematics was always have a backup route to your solution. So if you have time enough on the exam, or if you have time to do on your homework, you can just double check and always make sure you got it right by going the other direction as well. Okay, so hopefully that helps to fill in a little bit of how I check my work and how you can check your work as well. And if you're not familiar with that little last bit on the master theorem that I did, go ahead and check out one of my other videos on the master theorem and come back and see if that fills you in a little bit more. Okay, thanks a lot, and we'll see you in that next video.